Very good morning to everyone. In this lecture, EC 8791 Embedded and Real-Time Systems, Department of Electronics and Communication Engineering, 7th semester, Unit 5, Process and Real-Time Operating Systems. In previous session, we are discussing the introduction of multiple tasks and multiple processing techniques in embedded system design, and also the what are the parameters under terms of multi-rate systems and real-time operating systems in embedded design. And also we discussed the priority based scheduling techniques. Now today's session we are going to discuss the inter-process communication mechanism. So this is a internal processing and also the external peripheral, that is a co-processors. For example, we are using the processor of ARM7 or ARM9 or Cortex V4 processor families. So we are adding the external device peripherals or co-processor, that is a 80863 or 80862. So we are communicate through the interrupt request and acknowledgement through the datas. So we have to focus on the inter-process communication mechanism only. So that's the reason of this operating system. How to um interface the other devices, moreover the hardware equipment, and also how to support the software mechanism in also we are discussed in today's session. So what is the inter-process communication mechanism? It is a operating system as a part of the process abstraction, first of all. Then it is a two way of communication, that is a blocking communication mode and a non-blocking communication. The blocking communication, the process goes into the wait state until it receive a response. So the response may be the data to receive the other output, other, that is the input and output modules of the devices or systems or different operating methodology. So the second non-blocking communication, it is allows a process to continue execution after sending the communication. So that different type of inter-process communication, that is one of the SAD memory communication, second one message passing, third one signals. So here the SAD memory communication, it is a inter-process communication. It is used by a bus-based system methodology. That is the CPU and an input-output device. It communicate through a SAD memory location. So we are using the different memory locations in our processor, different registers, different vendors. So each individual locations we are address label to enhance the storage memory management system. So here the software on the CPU has been designed to know the address of SAD location. It has been loaded into the proper register of the input output device. So the CPU want to send the data to the device. It write the SAD location and read the SAD location also, etc. Now the input output device then read the data from that location. The read and write operation are standard, and it has encapsulate in the procedural interfacing. we can see the block diagram of how to share the data in the memory location into the CPU and also the input output peripheral devices. It is interconnected with the buses. It is a shared memory location. We can interconnect the read and write operation from the CPU and also the input output device. So we can using the buses. Now we can enhance the data, that is the CPU and also the input output device want to communicate through a shared memory block, that is a blocking communication and a non-blocking communication mode. There must be flag that tell the CPU when the data from the input output device is ready. The flag values of 0 when the data are not ready and 1 when the data are ready. If the flag is used only by the CPU, then the flag can be implemented using a standard memory write operation technique. If in case the same flag is used for bidirectional signaling between the CPU and also the input output device, and care must be taken from the secured communication methodology. So we can see the care, we can consider the following scenario to call the flag. That is our first point. CPU read the flag location and sees that it is a 0. The input output device read the flag location and see that it is a 0. The CPU set the flag location to 1 and write the data to the SAND location. And also finally, the input device errors set the flag to 1 and override the data left to the CPU. These are the function of the call flag operations. Now we can move to the elastic buffer as shared the memory. So in memory location, we have to share the data from the CPU and also the input output, so many devices, peripheral input output devices. We are using the memory. Here the buffer looped, elastic buffer looped methods. It is a text compressor is a good example as a shared memory. What is a text compressor? The text compressor uses the CPU to compress the incoming text, which is then sent on a real line of a universal asynchronous receiver transmitter, and also the input data arrive at a constant rate and are easy to manage. But the output data are consumed at a variable rate, so these data recorded as a elastic buffer. The CPU and also the output you are shared in memory area. The CPU write compressed character into the buffer and you are remove them as the necessary to fill the serial line. Because the number of bit in buffer changes constantly, the compression and the transmission process need additional size informations. So the CPU write at one end of the buffer and the UART read other end of the buffer. This only challenge is make sure that the UART does not overrun the buffer. Then another one is a shared memory communication is a message passing. So each communication entry has its own message sent or receive the unit. The message is not stored on the communication link but rather at the sender or receiver at the end point, the home control system. It has a one microcontroller per household device, that is a lamp, thermostat, hose and appliance. The device must communicate relatively infrequently. Their physical separation in large edge that we are good not naturally think that them as central pole of memory. So we have to pass communication packet among the device is a natural way to describe the coordination of the shared memory communication in the CPU to CPU. Then the third way of signals. Signals is generally the signal communication used in Unix. A signal is analogly to an interrupt. It is entirely software creation. So a signal is generated by a process and transmitted to another process by the operating system. So the UML signal is actually generalized of the Unix signal. So this signal is carried no parameters other than the conditions code. So we can easily to understand and reliable to transmit or share the datas. So UML signals is an object. There is a carry parameters as object attributes. The sign behavior of the class is responsible for through the signals as indicated by the send, or the signal object is indicated by the signal. So these are the some classes and the sign behavior in terms of the memory location. We can send or receive the signals to the integer or any other peripheral node. So in this lecture we are discuss the interprocess communication mechanism, how to the communicate in the CPU to other peripheral devices, and like interprocess communication, shared memory and message passing and signaling methodologies. And also what is the techniques, that is we are using the elastic buffer as a memory shared mechanism, and also message passing technique, and also the signal, how to the signal pass through the CPU to another classes of interfacing units. In upcoming session we are going to discuss the evaluating operating system performance in real-time embedded system. Thank you for watching this video.